Welcome back. This is lesson 2 of the series on stochastic processes. In lesson 1, we defined the Markov property and saw that a Markov chain is a discrete time process on a discrete state space whose next step depends only on the present state. In this lesson, we put the idea to work. We collect the transition probabilities into a matrix, discover that moving n steps is simply a matter of raising that matrix to the nth power, and then we handle the case where even the starting state is uncertain. And we finish with 2 worked examples that show how much these 2 ideas can accomplish. So let's talk about the transition matrix. In this matrix, which we call T, we collect every transition probability. Row I holds the probabilities of leaving state I. Each row is a discrete probability distribution, so they have to sum up to 1. Pij is the ith row, jth column, and then we're summing over the columns for a given row, so that this is basically the row sum for row I. And each probability is greater than or equal to 0. A matrix was, and then in general we have a definition here. A matrix with non-negative entries whose rows sum to 1 is called a row stochastic matrix. So our matrix T is row stochastic. Then I just have a sort of a summary of this, how to view this matrix here. Rows are the state you are leaving, columns are the state you are entering. So for example, row 2 gives every way of leaving state 2. And as I just mentioned, the rows must sum to 1 and the columns don't need to. So we have an example here. It's a random walk. It's just a one-dimensional, so either you go left or right, and this is the matrix. So you have the states are numbered from 0, so this row represents 0 and leaving, going back to state 0 is probability 0, but the probability of going from state 0 to state 1 is 1. And then probability going to any other states is 0. Then if you're in state 1, the probability of going back to state 0 is 2/5. There's no probability of remaining in that state, but there's a probability of 3/5 of going on to state 2. And then the pattern just continues here. So you can see there's sort of a drift. There's a higher probability of continuing to move further to a higher state, assuming those higher states are just to your right. And also, if you can't remain here, if you ever, even though it's less probable, if you venture back to state 0, you're going to get bumped out to state 1, and then you're into this again here. Okay, so that's a simple example. Let's continue. So here it gets a bit more interesting. If we want to move n steps, I probably shouldn't say it once, but if we want to move n steps, we want to know the probability of going from a state, I have it written down here. If you want to know the probability of going from state I to state j in n steps, then we write it here as Pij n. This is not to the power n, but it's just a notation we use here. And you notice this is time homogeneous. It doesn't depend on what k is. All we're interested in is going from state I to state j in n steps. And k could be 0, 1, 2, it could be anything, any integer, positive integer, or 0. Now, the interesting part is, and I'm not going to prove it here, but the Chapman-Kolmogorov result is that if we take our matrix T that had, these entries Pij in the ith row, jth column, if we raise that matrix to the nth power, we actually get these probabilities. We'll see an example of this in just following this slide here. So n-step behavior costs you nothing other than just raising t to the nth power. We need to be careful here. This counts all paths from I to j and n steps. So why am I saying you need to be careful? Because you could go, if you're going, let's take n to be 50. So and so you could go from state I to state j, and at the 10th step, and maybe at the 35th step, and at the 50th step. This is just giving you the probability that you're at the 50th transition, you're actually in state J, and it's quite possible you've been there before in less than 50 transition. There's another more difficult probability to compute that if you're in state I and you want to know what's the probability that the first transition takes place after a given number of steps. That's another calculation which we'll do later in lesson 6. And we have our example. I took the matrix T from a few slides back, and we wanted to know the two-step probabilities. So we had to raise T to the second power. And then to read this is pretty straightforward. I have an example here. Entry 2, 2. Remember, we're starting labeling these from 0. So it's 0, 1, 2, 0, 1, 2. So entry 2, 2 is here. And it's telling us that there's a 12/25 chance of leaving state 2 and being back at state 2 2 steps later. So that could happen by either going right and then left, or left and then right. So there's two different ways that could happen. Okay, and these all have the same type of interpretation. So far, every probability that we've discussed was conditioned on a known starting state. So if you recall, these Pij was the probability of going from I to j in n steps. So we kind of know where we were starting. However, you may want to ask the question, well, given the process starts at time 0, what's the probability that it's in a given state n steps later? And since we don't know what the starting, or we may not know what the starting state is, then we have probabilities. So that's what this is shown here. The probability that you start in state 0, the probability at time 0 you start in state 1, the probability you start in state 2, and so on. Now, if you do know exactly what state you start in, you could just have one of these equal 1 and the rest equals 0. So you can cover that case too. But more generally, you may just have a probability distribution for where you started. And the nice part of this is if you take this row vector and you multiply it times t, the matrix we've been talking about, t to the n power, then this gives you the absolute probability that at step n you're in a given state. You just need to, if you want to know the probability you're in state j, you would just take the jth component of this vector here. And remember, this is a row vector times a matrix, so this would also be a row vector that you get when you multiply these two together. Okay, so this may be not immediately apparent. It comes from this summation here. So if you multiply this out, you get each one of the terms in this row vector is this sum here. So in other words, the jth term in this vector is this term here. But I can show it a little bit more clear in the next slide, where I actually expand out these two vectors in this matrix, and then I'll show you one of the multiplications. It's basically the law of total probability, and let's have a look at that on the next slide. So here's the equation, the matrix vector equation I showed you on the last slide. P0, t to the n, and then p to the n. And then I've just written out the details, or at least part of the details for each one. And what we want to do is find this pjn, in other words, the absolute probability of being in state J at step N, given this distribution of probabilities in terms of the starting state. So you multiply this times the matrix. That's just from basic matrix multiplication to get the jth component. So this row times the jth column gives you the entry J in Pn. And then if you look at the details of this, it's the probability you start in state 0 and then that you go to state J and then at step N, or, and you add that, the probability you start in state 1 and you go from state 1 and into state J at step N, or you start in state 2 and then you go from state 2 to state J at step N. And so this is basically computing all the probabilities of starting in any of the possible states and then at step N being in state J, which is what we want. So that's the absolute probability of being in state J at step N. Right, so it's very useful, and this is all matrix multiplication, and then to compute a particular term, you just have this type of computation here. So let's look at our example that we had done earlier. If you recall, we had a matrix T, a transition matrix, and we squared it. I just carried it over here. So let's say that we know the probability distribution for the time 0, and there's a 1/3 probability of being in state 0, a 1/3 probability of being in state 1, and a 1/3 probability of being in state 2. And of course, these have to add the 1, so all the other entries are 0. And then if we want to find the absolute probability in it's step 2 of being in the various states, we just multiply this p sub 0 times t squared. So we could do a couple of these. If we multiply this times this, we get 1/3. That would be times 10 over 25. So it'd be 10 over 75. And then this is 0, and then this term would be 4 over 75. And so you get 14 over 75. And you can multiply this times this, and you notice that these two just give you 0. It's just the middle one that gives you 16 over 75. Then here, for this term, it's 1/3 times this plus 0 plus 1/3 times this, so it's 27 over 75. And then the next two, you're just going to get one term, 1/3 times this and 1/3 times this. So you get 9 over 75, 9 over 75. And then everything further out, you have zeros in these first 3 rows. And so when you multiply it by times this, you're just going to get zeros. And as a check, we could just add these, and they do add up to 1. So that's good. So these are the absolute values of being in a given state at step 2. So for example, the probability of being in state 2 at step 2 is 27 over 75. And probability of being in state 3 is, or 4, but it's the same, 9 over 75. And then anything beyond that, the probability is 0. And you can see why that might be the case, or that is the case, because you just don't have enough time to move from one of these 3 starting states further out than state 4, because you're just moving one, at best, you're moving it one state to the right at each, and there's still a probability of going back to the left. Okay, so it's pretty easy. You just, once you compute the transition probabilities, then everything after that is raising that matrix to powers. And then of course you need to be given what are the starting states. And after that you can compute these probabilities of being in a given state after so many steps. So let's apply our theory to a particular problem. We have a container that has two balls. They're either white or black. And we have the following rules here on the left. So a container holds exactly two balls. At each step, draw one ball at random, and that would be 50% choice of probability, I should say, of picking either one. Replace it with the same color was probability 0.6. Replace it with an opposite color was probability 0.4. The number of balls stays at 2 throughout. So we can model this as a Markov chain. There's no memory. It just depends on the current state. We'll let the random variable x sub n be the number of white balls at step n. The states are 0, 1, or 2, right? You could either have 0 white balls, 1, or 2 white balls. The color mix is all you need to know. And as I mentioned, the past is irrelevant, so it has the Markov property. And I have our transition matrix here. If you want to compute this as an exercise, I would pause the video here, and I'll come back in a second and give you the explanation of why these probabilities are what they are. Okay, so let's look at the transition matrix. So here in the first row, we have 0 white balls. So of course you have to, when you do the selection, you would pick a black ball, and that would remain black with probability 0.6, which means you would still have 0 white balls with probability 0.6. Or if you replace the black ball with the white, you would have 1 white ball at the next step, and that would be probability 0.4. The bottom row is also fairly easy, so let's do that second. So now here you have 2 white balls, so you have no choice but to pick a white, and you would replace it with probability 0.4, so you would go down to 1 white ball, or you would replace it with the same color, another white ball, and then that means you would continue to have 2 white balls at the next step. So that would be probability 0.6. So the middle row is a little bit more complicated. You have multiple cases here, especially for this middle one. So let's look at this here. We have 1 white ball, and we want to go down to 0. We want to compute the probability going down to 0. So you would pick that 1 white ball with probability 1/2, and then you would replace it with probability 0.4, and that would give you 0.2. The middle case is a little bit harder. You have 1 white ball, and you want to remain with 1 white ball. So either you pick the white ball, and you keep that with probability 0.6, so that gives you 0.3, or you pick the black ball, and you keep that with probability 0.6. So again, you still have 1 white ball at the end of the step. So you have 1/2 times 0.6 plus 1/2 times 0.6, and that's 0.3 plus 0.3, and you get 0.6. Then the last case here, you have 1 white ball, and you're going to go up to 2. So the way to do that would happen is for probability 1/2, you pick the black ball, and then you replace it with probability 0.4, so that's 0.2. Okay, so nice exercise in computing some probabilities. On the next slide, we'll look at what happens after 4 steps. Here's the matrix from the previous slide raised to the 4th power. So this gives us the probabilities of going from one state to another in 4 steps, and then I just have some, refer to them as questions, but they're just a matter of identifying the right thing in the table here. So what's the probability of having, um, starting with 2 whites, so you're down here, and then you end with 2 whites, it's 4 steps out, and that would be 0.3152. Then the second question is if you start with 1 white and you end with 2 whites, so that would be 1 white and you end with 2, so that would be this entry, 0.2496. And then third question is you start with 0 whites and you end with 1, so that would be this entry here, 0.4992. And of course you can ask other questions, but I just gave you 3 examples. So this is just using the theory we had about raising a transition matrix to a power, and then that gives us the probabilities of going from one state to another in so many steps based on the power you've raised the matrix to. Let's continue with our problem concerning the 2 balls black in the container. I have a different question. If we start with 2 white balls, what is the probability that the 5th ball drawn is white? Okay, so I'll leave this as an exercise. If you want to give it a try, pause the video here, and I'll come back and I'll give you the solution on this same slide. Okay, I'm back. So the solution depends on our transition matrix. We need to raise it to the 4th power in order to find the probabilities that there's either a 0, 1, or 2 white balls at the 4th step. You notice the first index is 2 in all cases because we're told that we started with 2 white balls. We just don't know how many are there at the 4th step. But we know the probabilities of that from what we computed on the previous slide. So we can just plug those in here. Then there's just a little bit more to do because if there's 0 white balls at the end of the 4th step, then the probability of drawing a 5th ball being white is 0. So this term drops out. If there's 1 white ball, and of course that means there's 1 black ball, the probability of drawing a white on the 5th draw is 0.5. Then if there's 2 white balls, of course you have to draw a white there, so the probability is 1. So we just plug in our numbers from the entry 2, 1 and 2, 2 on the previous slide, and then just do the calculation, and we get the 0.5648. And that's our solution. And then as a check, and I guess as another exercise, the same calculation for black gives 1 minus this number here. But you may want to just do that directly in a way similar that we've done that here. Okay, so let's continue. We're almost done. I'm going to just summarize this lesson on the next slide and then give you a little preview of the following lesson. So takeaways from lesson 2. T, the transition matrix, collects all 1-step probabilities. The rows sum to 1. N-step probabilities are gotten by raising a t to the nth power. And if you don't know where you've started and you have a probability distribution for the starting state, I should say, which is this vector here, this row vector P0, then you can just multiply that times t to the n, and that gives you the absolute probability of being in each of the states after n steps. That's this Pn here. And we've done an example of this. And then we saw on the example on the last slide, condition on the state, the answer questions that the matrix doesn't cover. So that was just a reference to our example. And then coming in part 3, or lesson 3, I'm using part and lesson interchangeably. The gambler's ruin problem, the most famous application of these ideas, so we'll be talking about that. You can imagine what this might be. A gambler has so much money and probability of winning and losing, and then you want to figure out the probability the gambler is eventually going to go broke. We'll set it up as a random walk, this problem here, with two absorbing barriers. Absorbing means either the gambler goes broke, or in the case the gambler is against, say, a house that has a finite amount of money, if the gambler wins all that money, which of course doesn't happen, but if you, say, for example, have two people playing against each other, that could happen, where the game is over when one side runs out. So those are the two absorbing barriers. Deriving the probability of ruin using a difference equation, and then we explain why the answer depends so sharply on whether the game is fair. Okay, so if you like this, please remember to give it a thumbs up and stay tuned for well, hopefully 10 more lectures. That was my plan. I haven't done them yet, so we'll see. But right now I have a plan to have a total of 12 lessons in this series.